Hello again. This is the last video for the course and the last video for differential calculus. So we are going to talk about optimization today. This is lesson 12.10, so let's get started. What is the definition of optimization? It's simply finding the best solution to a given problem. It usually involves finding the maximum value or the minimum value of a certain function. So let's go through some examples. I have a piece of metal. It is 500 centimeters by 300 centimeters, and I've got a square being cut out of each corner so that the sides can be folded up to make a box. So what size should those squares be if I want to maximize the volume of the box? So there's my piece of metal there. It's got the little squares cut out. Each square, I don't know how big it's going to be, so I'm just going to say that it is x by x. So what that means is the length of the box is going to be 500 minus those two x's that got cut off, and the width of the box is going to be 300 minus those two x's that got cut off from the top and the bottom. Okay, so that's the length and the width of the box. The height of it, once I fold those sides up, those sides are going to have a height of x. So now I can figure out the volume of the box. It's going to be the length, 500 minus 2x, times the width, 300 minus 2x, times the height, which is just x. And if I expand all of that out, I get 4x cubed minus 1600x squared plus 150,000x. So that's another way of calculating the volume of the box. To find the maximum volume, I'm going to take the derivative of that and see where it's equal to 0. That way I'll find a maximum of the function. So v prime, the derivative of 4x cubed is 12x squared. The derivative of minus 1600x squared is minus 3200x. And the derivative of 150,000x is just 150,000. So I need to set that equal to 0. I'll use a calculator to do that. It's not very pretty. So when I do plug that into a calculator and I look for the zeros of that function, they are at 60.7 and 206. Now when I get those values, I want to make sure that they both make sense. Does it make sense for me to cut squares off that are 60.7 by 60.7? Yes. Does it make sense for me to cut out squares that are 206 by 206? No, because one of the sides is only 300 units long, and you can't cut 206 from either side of that. That would be 400 and something, and there's not even that much of a length there or a width there to deal with. So I'm going to rule that one out, and so the only solution I can work with is 60.7, so that's going to be the size of the squares. Here's another example. I've got a man who is 2 meters tall. He's standing 3 meters away from a target that is 3 meters off the ground. He throws a ball, and the path of the ball is modeled by this function right here, y equals negative 4.9x squared plus 10x plus 2. He's not going to hit the target, but I want to see how close he's going to get. So I want to know the shortest distance between the ball and the target. Okay, so there is, what I've done is I've modeled the ball, the target with that little blue-green dot there, and I've modeled the path of the ball with that upside-down parabola. So I know that the coordinates of the target are 3 and 3. It's 3 meters off the ground, and it's 3 meters away from him. The coordinates of the ball are going to be at any point some x and some y, but I know how to figure out the y. That's going to be negative 4.9x squared plus 10x plus 2. So now I have to use the formula to figure out the distance between those. The distance between the x's is going to be x minus 3, and I square that. The distance between the y's is going to be that negative 4.9x squared plus 10x plus 2 minus the 3, that's the other y coordinate. And that has to be squared too. They have to be added, and they have to be square rooted, just like the distance formula always tells you to do. So I've got that function right there. I don't want to take the derivative of it, but what I can do is I can use technology to just find the minimum. So if I graph that function and I ask the calculator to find the minimum, then it can. It says that the minimum is at x equals 1.95. And so when that happens, the distance between those two things is going to be 1.06. So that's an example of how to use the derivative to find a minimum, and if the function's too ugly, you can just use your calculator to find that minimum for you. That's it for the lesson, that's it for the unit, that's it for the course. So if you have any questions, then for the last time, please let me know, and I will see you tomorrow.